Hopefully you have a little bit of a feeling now for what center of mass looks like for discrete objects, objects where you can break it up into a finite number of pieces. However, most objects that we care about in the real world are continuous. It's not just one ball or two balls or three balls, but a big old smear of mass. So we have to switch then from doing a sum to doing an integral. And the idea being in this case that we're going to break it up into little pieces of mass where it's an integral piece of mass, dm, and then again you're going to average over the different positions. So this can get a little bit challenging and largely is just integration practice. It's going to come up again when we do moment of inertia. So I want to look at one example to show you the basics of it. In my opinion, what's important here is that you understand what center of mass is and you have a feeling for it. I'm not, in general, I don't just assume, I don't assign a bunch of these calculation problems because in my mind that's more about practicing calculus than it is about practicing physics. So what does this look like? Let's look at a bar, it's a rod, and we want to find its center of mass in the x direction. Again, step one is defining your coordinate system. And so we're defining x equals 0 to be on the left end of the rod, and to the right is positive x direction. The rod itself has a length of L and a mass of capital M. So one of the first things we need to do is figure out how dm actually relates to position. The equation itself has dm in it, but you can't actually integrate over this. We actually need to integrate over position. So because of that, we need to get rid of dm. One of the ways you do that is by saying, okay, if I take my differential piece, that is some fraction of the total mass. This gets more complicated if your object isn't of uniform density, but we're not going to do that in this class. So our little piece is some fraction of the total mass. Proportionally, it must be the same fraction of the total length, right? Because it's a continuous, it's a constant density. So because of this, we can then rearrange and say that dm is simply capital M, total mass, divided by the length times dx. This is also like saying it's linear density times the length that you have, if that makes sense to you. So now we have our version of what dm actually is, and now I can relate it to a position derivative, which is what I want. So I then plug what I had here for dm. So I now have this m over L, and I have dx. I do a little bit of rearranging to pull m and L out front of the integral because they're constant, and you see what I'm left with in my integral is x dx from 0 to L. Okay, you know how to do this integral. This is not a hard integral. X integrated gives you 1/2 x squared. We then need to plug in the limits of 0 to L. And note that when we define the integral initially, we haven't defined any limits, but once you have a real situation, you know what the limits are in this case, right? It goes from 0 to L. That's important. These are always definite integrals. So when I plug in L to x squared, I get L squared. When I plug in 0, I get 0 squared, which is 0. So that leaves me L squared over 2L. Note that I then have L squared over L, which reduces this to L over 2. Does that make sense? Well, imagine taking a rod, this could be like a ruler or a very straight stick, and you're trying to balance it. You know that it balances over the center. The center of mass of a rod is in its center. That part makes sense. So we've done some math here to get an answer that we know, but one of the reasons you would do that is to verify that you understand the mathematical process. You look at this answer, you say, yes, this makes sense. Had you gotten something different, for instance, had you gotten L squared over 2, that doesn't even have the right units. This needs to have be a length, so it should have units of length. In this case, meters, for instance, if you're told what the length is. So this is the process. It obviously can get more complicated, but in general in here, we're not going to be doing the very complicated problems.